Great, thank you. I'm going to be covering some of the same material, but slightly from a different perspective, a little bit more from the regulatory perspectives. But I will, in keeping with the theme, I will be discussing the role of wind and solar generation to contribute to grid reliability. I will be providing a bit of a technical background, which remarkably doesn't overlap with what we've heard, and also talk about power purchase agreements and how they've been evolving to address this, and some recent FERC regulations, and a wind site that has received compensation for providing reactive power. So first, the technical background. This is just a summary of all the services that wind and PV can provide: active power controls, reactive power controls, fault recovery. I'm not going to go through the list because we've already heard a bit about this. But I will pause and go through this recent report that NREL did with Cal ISO and First Solar, looking at what are the reliability services that a 300 megawatt solar PV power plant can provide. This power plant is located in California. And let's see. And I want to highlight this. I know you can't read it, but I can give it to you later, and it's on the slides. Or you can just search it on the internet. But the website has a nice webinar, and NREL's website has a nice webinar that walks through this case study. So if you want to skip the Cal ISO background, you can go to like minute 20 and then really get into the details of this power plant. Sorry. So this is the grid infrastructure. I don't think I'm going to go into that detail, but I do want to look at this chart. Okay, there's a lot going on here, but this is part of the testing, the results of the testing that they did on this power plant. So let's see. Let's start at the top here. This yellow line is the voltage. This is the active power output of the plant. This is the reactive power. And this is the power megawatts on the left, voltage on the right, and time on the x-axis. So they're testing different types of frequency and voltage support that this power plant, the 300 megawatt power plant, can provide. So here we see active power plant. They are able to bring, with the system operator controls, they're able to bring the power down to 0, back up again. They have, are able to really finely control the power output based on what they're testing for. They are also able to use this power plant to consume and inject reactive power. And so you can see here as it goes up and down, and this is the impact of that on the voltage and on the active power of doing these reactive power controls. So they're able to really highly control this power plant. They're even able to provide reactive power at night by drawing on the current that's available on the system, so acting like a STATCOM. This is a test in the morning of AGC output. So they tested AGC control at different times of the day. So morning, this is the available megawatts as it goes up during the morning. And then they allowed it to have a 30 megawatt area in which it can control the frequency, the output of the plant. So the red here, I don't know if you can see it, but that is what the commanded set points are for that power plant. And then the yellow is what's following. And you can see how closely they align. It has a very high accuracy rate. So the accuracy is around, I think, 91%. And that's measured, Cal ISO measures that by, what are their, in 4-second intervals, what is their output summed up over a 15-minute period, and then what is the actual power plant doing. So using that metric, they have 91% accuracy rate. In comparison, a fast gas turbine has an accuracy rate about 30 percentage points lower. So very, like Mr. Suni was saying the other day, this has got, you can expect a lot from these power plants in terms of automatic generation control. Oh, the one other point I wanted to make is the accuracy it increases as you get more power plants providing this, because that error rate is associated with random changes in radiation. And so when you have more power plants providing AGC, then you have an even closer to 100% accuracy rate. Okay, we've heard a lot about wind, so I don't need to go into detail here, but wind obviously can provide these same grid services. This is a report that NREL did about 3 years ago to do a comprehensive stakeholder-based look at what is the responsiveness and different possibilities of wind turbines to provide active power control. So now let's get into power purchase agreements. So we've talked this morning about sort of what the systems can do, but they can only do it if they're required to do it. And so ways that we can require wind turbines and solar panels to provide active and reactive power control is to have it in PPAs, interconnection requirements, or if there's a market incentive. So carrot and stick approaches. So here is the stick side, or at least this is the negotiated side, but there's been efforts to try to standardize power purchase agreements for wind and solar, and I am hopeful that going forward that these standardized PPAs are grid aware and are inclusive of items that you would want a wind and solar plant to provide in terms of long-term higher penetrations of RE. So some of these are standard and have been around in PPAs, and some of them are more emerging. So here's just an example of what might be in a PPA in terms of the lower and upper bound of operational frequency that you would expect from an RE generator. So you want it to stay at the steady output within the dead band. Let's see. Also similar with voltage. You want the voltage, the nominal voltage, to be plus or minus 2%, for example. You don't want it to go too high or low and disrupt the utilities equipment. And this one has been around a lot, but low voltage ride-through. So this is very system specific. So these are different systems, like NERC is here in red, Hawaii is green, Puerto Rico is this blue, Ireland is yellow. So this is system specific depending on what the size is and other issues. But what you want these renewable energy generators to stay in that online in that no trip zone. So if there's a pretty big excursion and it lasts not very long, they can stay online. But of course, if the excursion lasts longer, we want to allow them to get off. Less a trend, but in the past, but more in the future, is to include very specific details on what types of data a central operator would need on forecasting. So either the provision of data that the system operator needs for centralized forecasting methods, or a decentralized actual forecast of power from that power plant. So the PPA might specify, well, first, the PPA would probably have to specify all the SCADA type equipment that's needed in the power plant in order for the system operator to have almost real-time visibility over what's happening at the plant. And so then to be able to do the forecasting, they need really good data, you know, what might be under repair, what is the height of the wind measurement, you know, what are the class of turbines so that we know the power output, et cetera. So this is increasingly in PPAs to specify this. And especially if we want the renewable energy themselves to provide ancillary services, then the grid operator needs to be able to see what's available you know, within 10 minutes time periods or so. If you want to get an example of a PPA, Xcel, which is one of the utilities in the United States, publishes on their website an example PPA. So you can actually look in here for language on, you know, how they address curtailment, for example, what's compensable, what's non-compensable, what are the rules requiring AGC, because Xcel requires automatic generation control of its wind, and then what are some of the provisions in terms of other ancillary services and how that will get compensated. We have also been active in the U.S. on changes to federal regulation in terms of the renewable energy providing grid services. So the big one last summer was FERC Order 827. And this rule requires that all non-synchronous generators be required to provide dynamic reactive power within the range of 0.95 leading to 0.95 lagging at the high side of the generator substation. And they are applying these requirements to any new non-synchronous generators seeking to interconnect to the transmission system. So FERC found that the old rules were discriminatory. They found that the controls that wind plants and you know, the smart inverters needed to provide grid services, the costs had come down a lot. And that it was, as the wind and solar are increasing in penetration, it would be discriminatory to not require the reactive power from these types of generators. So there's a lot of detail, though, in terms of what has to get negotiated. And so some of this is like the high side of the generator substation. So where do you actually measure the reactive power input? Do you measure it at the generating facility, at the high side, which is a little past some of the low voltage collectors and beyond some of the reactive power losses? Or do you measure it at the point of interconnection, which is the requirement for synchronous generators, but which would be farther away and therefore require different equipment for the wind generators to do? So they settled on the middle, the high side of the generator substation. They also were looking at who should provide this. So they settled on new. And so there are a lot of questions about, well, what if you're repowering? If we're repowering, do we require only the incremental new capacity to provide reactive power, or all the existing reactive power? What if you're somewhere along the internet connection queue and you've already bought your equipment, but you're not yet online? So all these details were worked out in this FERC regulation. And so I encourage you to, if you are interested in this type of work, to go look at the FERC document itself, because it summarizes all the rules in there, what the comments were from the generators, from the utilities, and then how they settled on decisions. We also had last summer FERC Order 828. This one wasn't talked about as much, but this one requires smaller generating facilities to also provide the same frequency and voltage ride-through events. So before, the rules were that, you know, these regulations apply to systems 20 megawatts or above. Now, these same, you know, if you're getting interconnected to the system, all those same requirements are, wow, that went fast, are required for small facilities also. This is acknowledging the fact that you have a lot more small systems coming online in the future. And again, you can go through the details about what some of the islanding concerns were and other technical details, but this is the settled. Finally, I wanted to give you a case study of a facility that is receiving compensation for providing reactive power. This is the Kelly Creek facility. This is a 184 megawatt facility near Chicago. It has 98 2-megawatt turbines. And they had been coming online right around when that new FERC order came out. They provide all these same services that, you know, I was talking about at the very beginning of the presentation. And one thing that's written about in FERC Order 827 is that there was not a clear methodology for compensating the provision of reactive power from wind. And so in the FERC order, it says any wind facility that's going to be applying for this must also submit and get approved the methodology for the compensation. And so I believe this is the first one that went through this process, this Kelly Creek facility. So the result is they had requested $1.6 million annually for compensation. They acknowledged that this was higher than synchronous generators, but they felt like with their lower capacity factor, it was a more equitable rate. However, the FERC, the ultimate ruling, I should say, was about half of that, $800,000 to annual compensation for the provision of reactive power. Okay, All right, so I'll stop there and take any questions or however you want to handle this.